Hi guys, so this video today is going to be on solving log equations, which I really like the concept of because two things. One is the whole reason we study algebra is to solve equations. That's literally the definition of algebra, is solving equations. So that's one reason I love this section. Also, it answers the question of why. Why do we even have to do this? Why do we have to know logs? Why do we have to? Well, because logs will help us solve equations. So just like if we have an equation that has addition in it, we would have to do subtraction to solve it. Well, if we have an equation that has an exponent in it, then we need to do logs to solve it. So to start off, I want to look at an old equation from a couple weeks ago, this compound interest equation. And so let's take a look at the problem. You invest $2,500 in BlackBerry stock in 2005. The stock proceeds to lose 5% every month. If the stock continues to decline at this rate, A, how much money will your stock be worth in 12 months? Okay, so this equation we learned a while ago. The A is how much you're going to have in the end. So that's what we're looking for. The P is the principal. That's how much you started with. And then inside the parentheses, we're going to put 1. And in this case, we are losing 5% every month. So we're going to say minus 0.05. And then T is how much time? 12 months. Okay, you will need your calculator today. So please get out your calculator and go ahead and put this into your calculator and see what you get. It is not nearly going to be as helpful for you if you're not doing the calculations. If you're doing the calculations, you'll be following along much better. Okay, so if you have put this into your calculator, you should get $1,350.90. So you're going to be losing some money. Now, the next question is, after how many months will your stock be worth $1,000? Now that is an equation that we have looked at before. We have answered questions like this before, but the way we did it was we went to our table and we scrolled down to our table until we got to the 1,000. That's just not very efficient because if it was like 800 months later, you would be doing a lot of scrolling. In addition, it's not very accurate because we're just like going, well, between years 23 and 24. So now we're going to talk about, well, how do you do it by solving? And so here's what we're going to do. Question is, after how many months will your stock be worth $1,000? So in this case, the $1,000 is now our A. So I can set up my equation similar to how I did before, but I'm going to put my 1,000 over here and my 1 minus 0.05 here. But now my exponent is going to be T, or M, if you want to call it M, whatever. And now we're going to solve this equation, and now we know how to solve this equation. First thing I want to do here is I want to isolate my exponent, so I'm going to divide by 2,500 because that way I can get my exponent by itself. And so on the left-hand side I have a 0.4, and then on the right-hand side these cancel out, and so I have a 0.95 to the t power. All right, well, how am I going to solve that? Well, I'm going to change this to log form, so rewrite this as a log. And what I mean by that is, do you remember how to do this as a log? This equation is a little bit backwards from how we've seen some of them. And so we've been talking about left, right, left. This one we're going to look at right, left, right, but that's okay. So the way we do it is we start with a log base. Well, what's our base? Our base was the base of the exponents. That's 0.95. Log base 0.95 of, we go to the other side, 0.4. is equal to t. And so now we can go to our calculator, plug this in using the log base function, and then work it out. Now, if your calculator does not have the log base function, I will get to that in just a second. But let's plug this in. If you do have the log base function, plug this in. Okay, so when you plug this in, you should get 17.86 months. So that is a new skill that you learned today. Congratulations, you just learned a new skill. You have learned how to convert a log, or excuse me, to solve a log equation and get an answer. So that's actually some pretty helpful and useful information. Okay, I said I was going to show you how to do it if your calculator doesn't have this function. This actually applies to everybody because not very long ago, No calculator had this function. There was not a button for this on the calculators. And I can say it was not very long ago because some of your classmates have borrowed their calculator from their sister or brother, and their calculator does not have it on there. So, I don't know, as of 5 or 10 years ago, most of the calculators could not do this. This is a new thing. And so how did we do it before? Well, we used this thing called the change of base formula. Because the calculators could do log base 10. Remember, there's just a plain log, it's log base 10. So they could do log base 10. What we do for this is, do you see this 5 is kind of down below? So we put the log base 5 down below. And this log 20 is kind of up above, so we put the log 20 up above. And so if you put this into your calculator, log of 20 over the log of 5, you should get the same answer as the log base 5 of 20. So here I have it on my calculator. I've got the log of 20, the log of 5, and I divide those. Or I can take the log of 20 divided by the log of 5, and I get this. And you would get the same answer if you put in log base 5 of 20. So this change of base formula is actually quite helpful. So that change of base will give us approximately 1.861. It's approximate because it was a decimal and I rounded, but that is what it will do. But you can use that if you don't have that button. But also, even if you do have that button, it's a helpful thing to know because sometimes you can change some equations around and maybe look at them in a different way if you understand this relationship. All right, but the main emphasis of our lesson today is solving a variety of log and exponential equations. I'm going to go through several examples. Starting with the first method is creating the same base. We had a little bit of practice on this a few weeks ago. If you look at 27 and 3, couldn't we create a same base, a common base for that? Because 27 is really just 3 to the third. So I can rewrite it that way. And now, since I have a common base, I have the same thing on each side, I can actually drop off the 3 and just say 3x is equal to x plus 5. So now I'm going to subtract that x, and I'm going to divide by 2, and I get x equals 5 over 2. So that's creating a common base. Can you take a second to look at number 2 and see if you can do that for number 2? All right, on number 2, the common base is 2. 16 is the same as 2 to the 4th. So I can rewrite this as 2 to the 4th to the x power. Then drop off your 2's. You have x minus 7 equals 4x. Subtract 3 from both sides. Divide each side by 3, and you get negative 7/3. So that is one method, is creating the same base. And that's a very effective method if you kind of coincidentally have numbers which have the same base. So 27 and 3, they have the same base. 2 and 16, they have the same base. What if they don't have the same base? All right, so let's look at these next examples. So on these, as I was going through here, I think we're going to skip part C on both of these. What I've done is I've rewritten the same equation twice. We're going to use it once using the left, right, left loop rule. We're going to do it again taking the log base b of both sides. The third method was to take log base 10 of both sides, and I just don't think we need to do that method. I think we have enough with this that we can get a good start on this. When I solve an exponential or a log, I need to isolate it. So I have this plus 2. I need to get rid of that 2. In addition, another thing, I'm about to take a log, and logs and negatives don't really go together very well. So in addition to doing that, I'm going to divide by -1 on both sides. Now I'm going to use my left, right, left loop. Log base 7 of 18 is equal to 3x. So I know I'm running out of space here, but I'm going to come over here and I'm going to say log base, and I need the base of the exponent. The base of the exponent is 7. Then I go to the other side and I come back. Now, log base 7 of 18 is something that we can do on our calculator. And even if you don't have that log base button, we just talked to you about how to do that. So do that on your calculator and see what decimal you come up with. Okay, you should have come up with 1.485, and that's approximate. And then we're going to divide each side by 3. And so our final answer is x is approximately equal to 0.495. Okay, I did my best to scoot mine over. I should have scooted over more, so I'm sorry about that. But let's look at our next example, example 3b. We're going to take the log base b of both sides. Well, what's the log base b? Let's start this problem off again. We're going to subtract 2, and we're going to divide by 1. So I subtracted the 2 and got negative 18. I divided by negative 1 and got positive 7 to the 3x power is equal to 18. Okay, we learned a couple of weeks ago that logs and powers are inverses. They cancel each other out. So what I can do is I can take the log base 7 of 7 to the 3x power and set that equal to the log base 7 of 18. So I chose base 7 because 7 was the base of the exponent. And now what happens is logs and the log base 7 of 7, it just cancels out. Those because they are inverses, they cancel out. And so now what I have is 3x is equal to the log base 7 of 18. Log base 7 of 18, I just did that a minute ago, and that is approximately equal to 1.485. And so once again, if I divide by 3, I will get x is approximately equal to 0.495. All right, I want to talk a little bit what I just did. These two problems, if you just came back to your notes and looked at your notes, you might think they were pretty much the exact same thing. And they are, it's just how you want to think about it. So in the first setup, I went left, right, left, because some of you are really good about going left, right, left, and you know what that means, and it works. You can do that. In the second problem, I took the log base 7 of both sides. Just like you can add to both sides or square root both sides, you can also take the log base 7 of both sides. And so that's what I did. So that's the difference. You got the same answer. It looks really similar, but it's just a different approach. Okay, let's look at the next problem. This time we have e. So I'm going to talk about that e a little bit, but remember e does imply natural log. It's going to have something to do with the natural log. So what I'm going to do is kind of go, first of all, by going left, right, left, like I had done before. And so if I go left, right, left, I'm going to say the log base e of 24 is equal to x plus 1. I'm going to talk about that. Remember, log base, the base is the base of the exponent. So here's the base, that goes to the base, then we go to the other side, and then we come back. The thing is, I'm about to erase some of this because we never call it log base e. We just don't call it that. We call it the natural log. So now I have the natural log of 24 is equal to x plus 1. Well, natural log of 24, we can all do that on our calculator. Our calculators know how to do that. So put that into your calculator and get a decimal value for it. Okay, so you get 3.178, and then I'm going to subtract 1 from both sides, so I get 2.178. And that is my approximation, for the value of x. And again, I just have those approximately because it's a decimal that I took off the calculator and I rounded it. Okay, that's one way to do that problem. The other way, once again, it's going to look very similar, and maybe even if you came back and looked at it later, it might look exactly the same. But what we're going to do is we're going to take the natural log of both sides. Because just like I can divide both sides or whatever, I can take the natural log of both sides. And when I do that, the natural log and e are inverses of each other, so they cancel each other out. So now all I need to do is take the natural log of 24 on my calculator. And that one I just did a minute ago, it comes out to be 3.178. I'm going to subtract that 1, and I get 2.178. So once again, if you came back and looked at this, you might think it looks exactly the same, but there's a just slightly different viewpoint, a different approach. I want to make sure you have a couple different ways to go about things, because when you get in the middle of an equation, you want to make the decision of which way is going to work best for you. Okay, let's turn the page. Okay, I really like this because I think this is a really cool word. Exponentiation. What it means is we can create exponents. We can make this into an exponent. Before we do that though, I want to combine these, right? This is a plus, so I want to put these together. So I put them together as a multiplication problem. Now, exponentiation means I want this to be my exponent, and my base is going to be whatever that log base is. So that log base was log base 3. I put a really big 3 there, and I purposely made it really big because that's now my base, and this is my power. This is my base, this is my power. And so now, because of that same thing, those are inverses of each other, they cancel each other out. So now what I have is 5x is equal to 9. Where'd that 9 come from? Well, 3 squared is 9. Okay, now I need to divide by 5, and then I'm done. So that's exponentiation. I think, like I said, I think it's a really cool process that you can do. You can just create an exponent, which is pretty cool. Okay, I'm going to do 7b, but I'm going to use a different method. I'm going to go back to my left, right, left method because, I want to give you some options. So we have the log base 3. Again, I want to combine these into a 5x is equal to 2. Instead of doing that, if you don't like that exponentiation or it doesn't work in a certain situation for you, you can go left, right, left. That is, this is my base, 3 is my base, second power is equal to 5x. Left, right, left. Okay? So I get 9 is equal to 5x. I divide by 5, and I get 9 over 5 is equal to x. All right, let's try another one. Can we condense this? This is going to be log of, it's going to be a division and a power, x to the third over 2 is equal to 5. Let's do that thing of exponentiation. In order to do that, we need to know what is the log base. And when there's not a base written in there, what is the base? It's 10. So I'm going to take 10 to the power of this is equal to 10 to the power of that. I should have written a lot smaller. Okay, I wrote it smaller so I can fit a little bit more. My log base 10 and my 10 are going to cancel each other out. And so on the left-hand side, all I have is x to the third over 2. On my right-hand side, I have 10 to the fifth. 10 to the fifth is a 1 followed by 5 zeros. I need to solve this. To solve this, I'm going to multiply times 2 on both sides. So I get x to the third is 200,000. So I need to take the cube root of 200,000. And the cube root of 200,000, you hook out your calculator and you plug that in, and you get 58.48. So that is the cube root of 200,000. Okay, that was using the exponentiation. If I did it again, and this time I used the left, right, left rule, so now I'm going to have the log of x to the third over 2 is equal to 5. If I go left, right, left, my log base is 10. So I get 10 to the fifth is x to the third over 2. So once again, I have 100,000 is equal to x to the third over 2. I multiply both sides by 2, and I take the cube root, and I get 58.48. So once again, if you looked at this in a week, it might look exactly the same. It's just a little bit different way of looking at it. But exponentiation is something you can do. You can take something and put it to the power of whatever you had. All right, a couple more examples. One of the examples is the one-to-one property. Actually, a couple examples are the one-to-one property. So I can combine these. Go ahead and combine these and see what you get and see if you can figure out how to solve this. I bet you can do it. Okay, so did you combine this to be the log base 3 of 5x? And then did you see that there's a log base 3 on this side and there's a log base 3 on this side? So, I mean, what you've kind of done is you've exponentiated with a capital 3, a big 3, but basically those just cancel out. And so you get 5x equals 2. Divide by 5 and you get x equals 2/5. Let's take a look at number 2. Before you even write anything down, look at the problem and see if you see anything wrong with this problem. Okay, we have different bases. We cannot go any further. We can't solve this because we have different bases. Because what we would do is maybe take 3 to the power on this side and And what? 3 to the power on that side? It's not going to get us anywhere. So this one's not possible. You cannot do anything with it if you have different bases. I wanted to make sure we pointed that out just in case that comes up. Okay, these next 4, we've done a lot of examples together, so I bet you can do these. Take a little bit of time, work through these. I'm going to come back and explain them, but work through and see what you can do. I bet you can do a lot of them. Okay, let's see what you have. On number 1, what I did is I exponentiated. You can do it the other way. Actually, you know what? I'm looking at this. I didn't. I went left, right, left. So I knew that this was log base 10. So I took 10 to the 5th is equal to 3x plus 1. 10 to the 5th is 100,000. I subtract 1. I divide by 3. And I get x equals 33,333. Number 2, I exponentiated. I took 10 to this power and 10 to this power. Why did I choose 10? Because this is log base 10. So that gives me x squared over 3 is equal to 100. Because 10 squared is 100. Multiply by 3, take the square root, and you get approximately 17.32. Number 3, you have to combine them, so we combine them. Again, I exponentiated with an e, so I took e to the power of this, e to the power of that. This is 6 over 3x, and e to the negative second power on my calculator gave me 0.135. Now, with this fraction, to get rid of the fraction, I multiplied by 3x on both sides. So then I got this, I divided by 0.406, and I got my answer of x. Number 4, I again exponentiated, so I took 7 to this power and 7 to that power. That gave me 49 over here. On the left, I had to multiply it out. I had to take 2x minus 3 times 2x minus 3 and multiply that all the way out. So I subtracted my 49 and I have this trinomial. It's a quadratic. That means it has to be equal to 0. So I subtract my 49. With that quadratic, I then have to factor. So I went ahead and factored it. It looks hard to factor up here, but I can factor out a 4, GCF. And then that makes my factoring much easier. Now, when you get two answers, you might want to think about, are these extraneous? Because we know that there's some things that for logs are not going to work with negative numbers. But actually, if I plug each of these in, they will work because, for instance, the negative 2 especially, that might be kind of suspect because you get a negative 4 here, minus 3 is a negative 7, but then you square it. And since you square it, now it's back to being positive again, so they actually both do work. All right, we went through a bunch of examples. I do want you to write a summary. We've learned a lot of things here, and it will help your brain to remember how to do these if you can write some things down. So summarize what you learned today. Tomorrow we will obviously do some work on this in class.